So in this video, we're going to talk about oxymercuration, demercuration, reaction, and mechanism. Right. So we know that this follows the Markovnikov rule, in that we're pretty much adding water across a double bond. And so if we take this molecule, we add mercury 2 acetate, and then we add sodium borohydride. In the second step, this is the product that we actually attain. The hydroxy group being on more substituted carbon. Now, this carbon has one hydrogen, whereas this carbon has two hydrogens, right? So again, the carbon that has two hydrogens is going to be less substituted because it has more hydrogen. The carbon that has less hydrogens is going to be more substituted. And so we should expect that we get rid of the double bond and we add or hydroxy group on the more substituted carbon. Now, essentially, we're actually adding water across the molecule. And so if we really look, there's our OH group, and then there's our hydrogen that we added. There's also two hydrogens which I've not labeled, but again, these are the other two hydrogens. So let's talk about the reaction. The reaction mechanism is rather something they would probably not ask you in your organic chemistry classes because it's rather a complicated mechanism, but let's look at it anyway. The first thing that occurs is that the double bond of the alkene actually breaks a bond formed between the acetate and the mercury atom. Subsequently, this bond also breaks, giving the acetate a negative charge. Right? From here, the reaction actually proceeds into an intermediate step, right, where the mercury acetate is added on the more substituted on the less substituted carbon, with us forming that carbon cation. Right? This is in equilibrium in the intermediate step with a weird looking tricyclic molecule where the mercury atom is actually sandwiched in between. It gains a positive charge and is bonded to an acetate molecule. So this is the intermediate step. Now, which form is prominent? The intermediate step on the left. So the next step in the reaction, you actually have in the next step in the reaction, you actually have the acetate molecule attacking the carbon cation simultaneously as a water molecule attacks the carbon cation. So the acetate molecule simultaneously attacks the water molecule of the carbon cation. The water molecule attacks the carbon cation simultaneously with the acetate molecule. So as a result, what occurs? The next step in the reaction is that we actually add water. Right? So now we have an oxygen that's bonded to a carbon that contains one lone pair, 3 bonds. That's a positive charge. Right? And we still have the acetate lingering around on the less substituted carbon, the mercury acetate. Now remember, we said that we formed a negatively charged acetate in this junction, right? So we did form OAC minus. And so in the next step of the reaction, the negatively charged acetate comes in and acts as a base, takes all the hydrogen, form lone pairs on the oxygen. So essentially, this is the product that we get. We have the OH molecule now, but we still have our mercury acetate on the less substituted carbon. So in the next step of the reaction, we actually use sodium borohydride. Now, we could simplify sodium borohydride as really a source of H-. And it actually acts as a nucleophile, attacks the carbon containing the mercury acetate, and displaces it. So essentially, the final product is the molecule like we predicted before. So you can see that this is a really complicated mechanism, and it's something that your teacher will probably not like will least likely to ask you about, but they're more so they want you essentially to be able to predict the product. So not so much of the reaction mechanism, but it's still important to know the reaction mechanism.